Okay, we continue with the next proof. We want to prove that log of m to the small of n, base of logarithm is a, equals n times log of m base a. Basically, this is logarithm of a power. The exponent is n, the base is m, this is a power, m to the small of n. We want to say that logarithm of a power is equal to n times log of m base a. So the exponent becomes a coefficient for the logarithm itself, basically. That's what we want to show. So we are going to start by saying let the logarithm on the right-hand side, which is log of m base a, equal to x. So we let the logarithm on the right-hand side, which is log of m base a, equal to some variable x. And then we're going to use the definition of logarithm. We're going to write this in exponential form. So we're going to say a to the exponent of x equals n. All right? Then we are going to raise both sides of this equation by raise both sides to the exponent of n. So we're going to raise left side to the exponent of n and right side to the exponent of n. So we have m here, a to the x. So we end up with a to the exponent of xn equals m to the exponent of n, basically. Then we're going to say, okay, two expressions are equal, therefore their logarithms must be equal. So we take the log of left side and we take the log of the right side. The base of the logarithm, we choose it to be a. So log of a to the xn base a equals log of m to the n base a here. Now, I think we had a formula like this before, or maybe not. We can say the left-hand side is actually x times n, because the base a raised to the exponent of only xn will equal to a to the exponent of xn. So that's applying definition of logarithm. And on the right-hand side, we have log of m to the exponent of n. The base is a. Now let's not forget what x was. X was log of m base a, which I can substitute here. So it becomes n times log of m base a, which is equal to log of the power we're trying to find. Therefore, you see that log of m to the exponent of n is equal to n times log of m. As a numerical example, I can say log of 2 to the exponent of 5 would equal to 5 times log of 2. Any arbitrary base, you can say base 3, for example. So what you should remember is that the exponent of 5 becomes a coefficient for the logarithm itself. Okay, so now we learned this other formula. I'm going to write it down here. N times log of m base a. So that's another formula. It's called power law of logarithm. That's the name of it. Do we have other formulas I can think of? Perhaps I can give you another formula. Log of 1 over m equals negative log of m. And this is not very difficult. If you let me change m to n so that it would match with our formula that we proved previously. So this is m over n. Instead of m, I just plug in 1, and that becomes a reciprocal. So I'm saying log of 1 over n equals log of 1, which is 0, minus log of n. So that gives you 0 minus log of n, which is negative log of n. Therefore, we can conclude that logarithm of a reciprocal of a number is negative logarithm of that number. So base can be arbitrary, any valid base. For example, log of 1/4 is equal to basically negative log of 4. Or you may say log of 1 over 12 is actually negative logarithm of 12. Any arbitrary base 5 would work. So that is logarithm of a reciprocal, which is equal to negative logarithm of that number itself, whose reciprocal was mentioned earlier. Okay, so we have 8 bubbles here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I want to make it 10. So I'll have to add more formulas here. Some of them may be in the book, some of them may not be in the book, but I want to add as many as I can. So the next one I'm going to use or show, it's called change of base formula. Okay, so if you have log of a to the base b, that's equal to log of a over log of b, any arbitrary base of m you can select, no problem. Okay, that's what I want to show. I want to show you what is log of a to the base b equal to, and we are going to show that it's equal to the quotient of the two logarithms. With any arbitrary base, I called it m. So I'm going to say let log of a base b equals x, for example. And from here, we get b to the exponent of x equals a. All right? And then I'm going to take the common logarithm of both sides. So we get b to the x equals log of b to the x equals log of a with the arbitrary base of m. And now we see that the exponent x could become a coefficient for the logarithm, as I explained earlier. So we get x times log of b base m would equal to log of a with the same base m. Now, if you solve for x by dividing both sides by log of b, you get log of a divided by log of b, arbitrary base m. All right? So this x is actually the same x that we had before, if you recall. Therefore, we can say that log of a to the base b equals log of a divided by log of b, and the base could be any arbitrary base. And this is called change of base formula. I'm going to add it to the list we had. So log of a to the base b equals log of a all over log of b, and the exponent could be any, the base could be any arbitrary base m. Now, what is the importance of this formula? The importance is the following. We have two buttons on the calculator. One is the common logarithm, and one is natural logarithm, which is ln. Now, we don't have a button for log to the base 2 or log to the base 5 or log to the base 6 and all that. So the question is, how can we find log of, let's say, 14 to the base of 13, okay? There's no button that calculates the base 13 logarithm. So we're going to use the change of base formula. I mean, let's say this is actually equal to log of 14 divided by log of 13 with any arbitrary base that we can select. We can select like this arbitrary base to be 10 because we have the button on the calculator, the common logarithm button that we have on the calculator. So we can press the LOG button and find log of 14, common log of 14 divided by common log of 13, which can easily be done actually. I can do it with the calculator. So I go log base 10 of 14 and I can divide it by log, again, base 10 of 13, for example. And the answer would be 1.0288. 1.0288 roughly. So log of 14 base 13 would equal to this number. But there was no separate button for finding logarithm of numbers with base 13 on the calculator, but I used this change of base formula to find the answer. Now, instead of pressing the log button, I could have done the same thing with the natural logarithm button. I could have said this is actually ln of 14 divided by ln of 13. It would give me the same answer. So this is the importance of this change of base formula. That's why manufacturers of calculators, they didn't design a separate button for log base 2, log base 4, log base 5, log base 6. They didn't design, they just put two buttons here, common logarithm and natural logarithm buttons on the calculator. Because mathematicians, or actually manufacturers of calculators, they knew about this change of base formula, and they said, why bother when somebody wants to calculate log of 14 base 13, they can use this change of base formula, they can press the division button, which is already there on the calculator, and they can quickly find the answer. So why bother, designing a separate key for log base 13 or log base anything else? So this is the other formula. And finally, perhaps if I want to add a 10th formula, I would say if you have more than two numbers in product form, so if it's n times p times q, just like that, and the base is of course a, if you have log of m times n times p, just like that, it's going to equal log of a whole bunch of product of numbers. It will be equal to the sum of the logarithms of those numbers. So it will be basically log of m plus log of n plus log of p, and then plus dot dot dot, and the base is the same a as before. So this is an extension of the product law of logarithm. Here we had only two numbers in product form, but I'm saying if you have 3 numbers, 4 numbers, 10 numbers in product form, the logarithm of those 10 numbers, the product of 10 numbers, would be the sum of the logarithms of those 10 numbers one by one. So you just have to add them all up. And that is an extension of this product law of logarithm. So now it makes it like 10. We have 10 laws of logarithm, and we just have to learn them very well, just like exponent laws, and we have to be able to apply them in solving different problems. Thank you.